Hi, I'm Mr. Tseve, and today I'll be teaching you mathematical induction. But what is a mathematical induction? Mathematical induction is a way of proving mathematical statements about natural numbers. And let me show you some steps on how to prove an induction. So we say that the proposition is true for Pn equals to 1. It is just an assumption. So if this proposition is true, therefore, then we assume that the proposition is also true for P into n equals to k. This is what we call inductive hypothesis. This will be our hypothesis. Then the proposition Pn equals to k plus 1 is also true if this hypothesis is true. This means that P into n equals to k, it is an implication of P into n equals to k plus 1. So if this statement is true, then this one is true. So this sign is for implication. It means that if this statement is dependent on this one. So if this statement is true, therefore this one will also be true. And then don't forget, guys, this is our inductive hypothesis. And then this is the statement that we are actually required to prove. RTP means required to prove. And this is the statement that we are required to prove using our inductive hypothesis. Now, let me just take an example. Suppose we are having a series like this. Suppose that we're having a series like this, and they're telling us that for all n is the element of natural numbers. So all this n, they actually belong in the universal set of natural numbers. So they gave us something like this, and they are saying that we must use mathematical induction. So for us to prove using mathematical induction, we are going to check this side of the formula. So we are going to assume that our n is 1. So if n equals to 1, therefore we substitute in here. So we substitute 1 where we see n. This is equals to 1. So if this is true, this is true. And if this is true for all n greater or equals to 1, therefore we have to make a hypothesis. So our hypothesis will also hold for k is greater or equals to 1 for all n which belongs in the natural set of natural numbers. But our k will be equal to n by our inductive hypothesis. So then we have to add k wherever where we see n. So this is the series that we are having. So where we see n, we add k. Even this side, we add k. This is what we are having. And this is our inductive hypothesis. And if this hypothesis is true, it means that n k plus 1 must also be true. So wherever where I'm seeing n, I'm going to substitute this using what we are given prior. So this is n, I'm going to put k plus 1. And even here, it's going to be k plus 1. And even inside, k plus 1 plus 1. So which is the same as 1 over 2 k plus 1 k plus 2. Like I said, this is what we are required to prove. But we are required to prove this using our inductive hypothesis. And this is our inductive hypothesis. Sorry, let me not erase my hypothesis. So, we are going to actually check this side, the left hand side, and equate it to this left hand side. And then add this term. Let me show you what I'm talking about, guys. So, is 1 plus 2 plus all the way to k plus 1 equal to this side. I'm equating left hand side. So it's also 1 plus 2 plus all the way to k. But since I have this term in here, I must also edit this side. But according to our inductive hypothesis, it is said that I think we have this according to our inductive hypothesis. And this part is equals to what? That part is this part. And is equals to this thing. So is 1 over 2 k plus 1 plus k plus 1. So I can actually factorize. So I will have k plus 1 into 1 over 2k plus 1. This is what I'm going to have. This is what I'm going to have. And this thing is equals to this one. That means it is proved for all n belongs in this natural set of natural numbers, whereby n is greater or equals to 1. So it is proved using mathematical induction. That was the simplest example. So let's take another example of this kind, but a little bit difficult. Let's take another series, guys. Suppose we're having a series of 1 plus 2 to the power 3, 3 to the power 3, plus all the way to n to the power 3 equals to n squared, n plus 1 squared, all over 4. For all n belongs in the natural set of natural numbers. Sorry guys. So we are still going to use our hypothesis. So we are going to say that we are going to assume that our n equals to 1 for n equals to is greater than or equals to 1. So we are going to substitute in here this one. So if we substitute 1 there, we get 1. This is what we are getting. So this is true. And if this statement is true, we can go and make our hypothesis. So our hypothesis will also be of whereby k holds, or whereby k is greater or equals to 1 for all n which belongs in the set of natural numbers. Therefore, our k is equals to 1. This is what we are having here. So I'm going to use this series, and wherever where I see n, I'm going to put k. So it's 1 plus 2 to the power 3, all the way to k third, k to the power 3. So where I see n, I'm going to put k, guys. This is what I'm talking about. And this is my inductive hypothesis. This is my inductive hypothesis. So if this hypothesis is true, it means that n equals to 1 plus k should also be true. So I'm going to use this sequence again, but wherever where I see n this time, I'm going to put 1 plus k. So it's 1 to the power 3 plus 2 to the power 3 all the way to 1 plus k to the power 3. Remember to put this power. Remember to put this power here because of I substituted in this n. So I'm also going to substitute 1 plus k on n on every n that I see plus 1. This is what I've substituted. But remember to square it according to the formula. So this is the same as 1 plus k squared, 1 plus, this is just k plus 2 squared, all over 4. So this is what I'm required to prove. RTP. RTP means required to prove. But how do I prove this? I prove this using my inductive hypothesis. So we are still going to do what we did last time. Last time, this is what we did. We said that this side is equal to this side added with this term. So it's 1 to the power 3 plus 2 to the power 3 plus all the way to 1 plus k to the power 3 equals to this term. 1 to the power 3, sorry about this 3 guys, plus 2 to the power 3 plus k plus, I've added this, this is k, but I'm also adding this term because of it also appears in here. So it's gonna be what? When I'm adding this term, I'm getting 1 plus k to the power 3. You take it the way it is, guys. So, but what is this? So according to our inductive hypothesis, that one, it's actually this. And this thing is equals to that one. Is equals to this thing. So I'm going to have k squared, k plus 1 squared, all over 4, plus 1 plus k to the power 3. So if I take out the common factor, 1 plus k squared is the common factor. So I'm going to have let me write here. I'm going to have 1 plus k squared over 4 plus x plus 1 plus k. This is what I'm having when I factor out. That's what I'm having. That's what I'm having when I factor out. So let me erase this part, guys. Let me erase this part. So if I multiply this by this one, I can just put 1 here and make the denominators the same. This will be the same as 1 plus k. If I multiply by 4, I'm going to have k squared plus 4k plus 4. I've multiplied by this 4. If I multiply this 4 by 1, I'm just going to have 4. But this is the same as, this is squared, guys, don't forget. But this is the same as 1 plus k squared into, if we factor this out, we're going to have k plus 2, k plus 2 all over 4. Let me erase this part because if I'm done with my hypothesis, the only one that I'm proving is this one. So since I'm here, we can see that 1 plus k squared into k plus 1 squared, because of this thing is equivalent to this thing, over 4 is the same as, let me erase this part again, is the same as 1 plus k squared, k plus 1 squared, all over 4. And we can see that this is equals to that one. Therefore, we proved it. It means that the predicate, P of n equals to k is implication of P, is implication of Pn equals to k plus 1. So we proved by mathematical induction. We can conclude by saying, okay, we proved for all n which belongs in the set of natural numbers. So we can conclude that n will be greater or equals to 1. So we're done. Let's take another example which is a little bit trickier. I can call this case 1. I can call this case 1 because of mathematical induction has 3 ways of actually providing you with problems. This is the case 1, part 1 actually, how they actually set the problems in mathematical induction. And then we are heading on to, okay guys, like I said, there are 2 cases. There are 2 cases that we actually have to take. So suppose that this is case 2. Suppose that you are given something like 7n plus 2 plus 8 2n plus 1. And they're telling you this thing is divisible by 57 for all non-negative integers. So, but we know the non-negative integers, they're actually from 0. They're actually from 0 to positive infinity. This is what we know according to a number line. This is what we know. So that means we have to substitute using trial and error method. We have to substitute from 0. So if I substitute 0 here, let me predict if n equals to 0. Let me assume. So it means that n is greater or equals to 0 also. So if I put 0 here plus 2 plus 8 2 0 plus 1, I'm getting 57. I'm getting 57. That means this thing is true. So if this is true, we can go back and actually make our hypothesis. If this is true, so then k is greater or equals to 0 for all k which are in the set of natural numbers. Therefore, k is equals to n. K is equal to n. So wherever where I'm seeing n, I'm going to put k. And this is our statement. So I'm going to put 7k plus 2 plus 8 2k plus 1 equals to 57. We assume this statement. So if it's like that, I can manipulate it a little bit and say 8 2k plus 1 equals to 57 minus 7k plus 2. You can actually set any term that you want. And this is our inductive hypothesis. This is our inductive hypothesis. And if this hypothesis is true, that means n for k plus 1, that means it's also true. So wherever where I'm seeing n, I'm going to put k plus 1. I'm going to this statement again. So it's going to be 7k plus 1 plus 2 plus 8 2k plus 1 plus 1, which is the same as 7k plus 2, plus 3 plus 8 2k plus 3 also equals to 57. And this is our LHS. And this is our RHS. So how can we prove that this statement is actually divisible by 57? We have to use our inductive hypothesis. Always, always, always. So, let me erase this part. So, I can actually rewrite this again in a manner like 7k plus 1 plus 2. Why? Because of I want to have k plus 2, which is k plus 2 here, so that I can substitute if I want. So I'm writing even this 8 in such a way that it's like this. So it's going to be 8 2k plus, since more is 1, I'm going to put 1 here, and plus 2. You see, I'm moving this term. So wherever where I'm seeing this, I can substitute this according to our inductive hypothesis. This is LHS. We are focusing on it right now. So, and this is a k plus 2. So I can just say k plus 2 times 7 1. So I'm having it appears here. It's a nice thing then, because I have to make sure that the exponents are equal so that they can add to each other or subtract to each other in the end. So this will be plus, but this is the same as 8 2k plus 1 times 8 squared. This is what we are having. So this is the same as 7k plus 2, and then this part, it's actually here on our inductive hypothesis. So we can just insert this wherever we see this. So it's going to be 57 minus 7k plus 2 times 8 squared. So we are done with this part. We can erase it. Unlike case 1, we are done with this part. Right now, what is it only required of us is to show that that sequence or that series, is divisible by 57. So I can multiply throughout here. I can multiply 64 times 57 is 48 minus, but this cannot multiply this one because of they are not the same. So it's 8, it will stick with it, k plus 2. But wherever where I'm seeing this, I can just say 7k plus 2 b. So I'm gonna be having something like 7, and here I'm going to substitute b, plus 3648 minus 8 squared b. So you can see that these terms are like terms. So I can say 7 minus 64, it gives me minus 57. So it's 3648 minus 57b. 57b. If I can factor out by 57 here, that means this thing is divisible. So let me try to factor and see. So what is 3648 divided by 57? So is divisible. This term is divisible. Even this one is divisible. So this one will just be b. So I can substitute my b. My b is just 64 minus 7k plus 2. So we have seen that this is actually divisible by 57 for all n which belongs in the set of natural numbers, whereby n is greater or equals to 0. So this is actually what we are having. So you are done. You have induced, and then we can see that this is true. Let's take another example of this fashion. So suppose that we are given 4n plus 1 plus 5 2n minus 1, which is divisible by 21 for all n equals to en. So you will do your trial and error. You assume first that n is greater or equals to 0, whereby n equals to 0. So, sorry, this is exponent, guys. So, if I substitute wherever where I see n by 0, this is what I'm getting. I'm substituting. So I'm not getting 0, I'm getting 21 over 5. Let's try 1, guys. So wherever I'm seeing 0, I'm putting 1. Four squared plus 5, 2 minus 1 equals to 21. So this is true. And if this is true, I can go there and make my own hypothesis. So, but this hypothesis will work that k is greater or equals to 1 for all, for all k's which exist in the natural set of natural numbers, whereby n equals to k. So everywhere I'm seeing n, I'm putting k. So it's going to be 4k plus 1 plus 5 2k minus 1 equals to 21. I can make this subject of the formula because of last time I made that part which was here. So it will be 4k plus 1 equals to 21 minus 5 2k minus 1. So this is my inductive hypothesis. This is my inductive hypothesis. And if it's true, that means n 1 plus k should also be true. So I'm coming back here. So wherever I see n, I'm putting 1 plus k. So I'm going to be having 1 plus k plus 1. This is the exponent, guys. Plus 5 to 1 plus k minus 1, which is the same as 4k plus 2 plus 5 2k plus 1, which is equals to 21. I'm having this. So this is the thing I am required to prove, but I will prove it using my inductive hypothesis. So we will focus on this left HS. So I can erase this part except of my inductive hypothesis, as I will need it. So this LHS equals to, I made this the subject of the formula, so I must write in terms of this exponents. I must write in terms of those exponents. So this one will be what? It will be 4k plus 1 plus 1, because of it gives me 2. And then this one will be 5, and then here I'm seeing 2k. It will be 2k, and then this is the same as 2k minus 1. 2k, yes, 2k minus 1 plus 2. This is what I'm. So when you are here, you can write this as 4k plus 1 times 4 1 plus 5 2k minus 1 times 5 squared. But what was my inductive hypothesis? My inductive hypothesis was 4k plus 1 equals to 21 minus 5 2k minus 1. This was my inductive hypothesis. So wherever where I see this, I can actually put that. So it will be 21 minus 5 2k minus 1 times 4 plus 5. I can just put this here. Let me erase my hypothesis. Times 5 2k minus 1. So exponents are the same. So I can multiply throughout. It will be 84 minus 4 times 5 2k minus 1 plus 5 squared times 5 2k minus 1 minus 1. So I can let b equals to 5 2k minus 1. So it will be 84 minus 4b plus 5 squared b. So and then this, when I subtract them, it will be 4 minus 25. Minus 4 plus 25, sorry, is 21. B is 21b. Sorry. But I can divide by 21 here. I can factor it out. It will be 84 divided by 21 is 4 plus b. But what is my b? My b is 4 plus, this is my b, 5 2k minus 1 for all n which belongs in the natural set of natural numbers, whereby n is greater or equals to 1. So this is the